So I'm Sean Armstrong. I'm the managing principal for Redwood Energy. We did our first zero net energy, all-electric, 100% solar-powered apartment complex in 2012. And then we did another one in 2012, and another one in 2013 and 2014. So I have a lot of experience. I did my first one in 2008. I designed an all-electric, 100% solar-powered apartment complex. So what that looks like, my professional background is I got trained at a demonstration house at Humboldt State University's campus, started in 1995. It was off-grid, it was solar-powered. I put in a wind turbine, a 2-kilowatt PV array. Pamela Bartholomew started a biodiesel refinery in the yard we were together at the time as friends. And so my next job was as a science teacher. I'm a professional scientist. That's how I consider myself, a fact-based person. And I then spent like 6 years as a construction project manager. I couldn't get a job as a science teacher. Schwarzenegger messed up everything with getting jobs for teachers. So my background is as a professional construction cost value engineer. My job was to make sure the project was the least cost, first cost, if at all possible. However, I got there hook or crook. I did, 10, 15 different developments that process. And the consequence, since I went into a consultancy with Michael Winkler, who is a physicist, he was the technical lead on the world's first cell phone system back in the day. We've done about 5,400 solarized units. We've got about 70 projects. And then zero net energy on the other side there, you can see more than 2,032 projects. And that was last year's data. We've done a lot more since then, but it's hard to keep up. Okay, so why that is, if you look nationally, since 2010, the market share growth is in all-electric construction. Nationally, it's not a political thing. It's a first-cost development-based, how do I get a building permit decision? If you want to get a building permit, the cheapest way to get a building permit, and first cost dictates in construction, it's cheaper to go all-electric. That's a national phenomenon. It dates back at least till 1993, when the EIA started noticing an uptick. It's been centralized in the South. Since 2010, though, that's an important year, because that's the first year in the United States we got heat pumps that had inverters on them that would go to colder and colder temperatures. So now they're building all-electric developments above the Arctic Circle that are zero net energy, solar powered, over a year. So we're going to use site definition, kilowatt hours in, kilowatt hours out. So in that scenario, you can see now in the South, 1 in 2 homes are being built all electric. 1 in 4 in the United States. The increase in growth is rapid. And it's because it's cheaper to build. In California, what we've seen is, on the left-hand side, these are 2 of our commissioners. And they had approached some of the big developers, and they found that it saved them $4,500 per residence to not put in gas. On the right-hand side, you can see another one of our commissioners who's saying, the proposed refurbishment is not a good use of ratepayer dollars, canceling gas peaker plant. We're establishing it's not cost-effective. It's too expensive on the first cost, actual money. Not politics, it's too expensive to go this route with gas. Now, I want to elaborate on that. SoCal Gas had to submit costs for extending gas services to new communities in the San Joaquin Valley. They found that the gas lines to go in, $66,000 per unit, per household, $83,000, 12 grand, 5 grand, 30 grand, 5 grand. This is what it looks like to extend gas services to houses that don't have it yet. You can also imagine it's at least that much to maintain the gas line that's in the ground. Disturbing an existing road requires tons of flagging so that people don't get killed working there. And so it is at least twice as expensive to maintain a gas line as it is to put it in new. Far more labor, far more interventions, and you can't turn off gas. You have to weld on it hot. So you pinch it with the backhoe, and then you weld it shut, and you have a bunch of guys down there hoping they don't blow up. So once you get into the building, you find that it's, in the range of, the lateral, I forgot that one. It's another $5,000 to $15,000 to just put in the lateral, not the gas mains, just the lateral. And then you can go down to what it costs inside the building. Every single gas appliance fixture is going to take $300+ to get the gas line to it. Then you have to buy the device. A furnace with an air conditioner is far more expensive than a reversible air conditioner. Reversible air conditioner, an air conditioner costs $1,800, say a 3 ton. That's an $1,800 device. A heat pump is then $2,000 because all they have to do is put in a new valve, a reversible valve, and a reversible pump. Very small increasing incremental cost to an air conditioner to make it reversible. But if you put an air conditioner and a gas burning box next to it, it goes up $1,000. You can find this in Rheem, you can find it in Maytag, you can find it in any manufacturer you want. Adding a gas burning box is far more expensive than making a reversible air conditioner. Then you have to get rid of gas fumes. And it's going to cost you products you can see there, a few $100 into products, and it's going to cost you at least that much in labor to get the thing through the wall. So you see on-demand gas water heaters inside of a house, for instance. It takes $1,500 to get it all the way up to the roof to evacuate it. If it's on a wall, maybe it's only a few $100s. But it's always more money than putting in a heat pump, which requires no exhaust of dangerous fumes. So in the real world, I service developers. I don't work for utilities, I don't work for policy folks. I'm just working with people who care about first cost. So in a first cost, real world, there's 100 apartments here in an apartment complex in Sacramento. There's an existing gas wall heater, there's an existing PTAC, a packaged terminal air conditioner, a little through-wall thing. And they went to a higher performance air conditioner with an electric resistance heating element on it. So they had to put in a new electric line to that. They could have done a heat pump, they decided not to because it's cheaper to go this route. And they still saved $800 per residence by not having to put in a new gas wall heater. You can see the cost for gas wall heaters there. It goes, the actual device is about $1,500 to buy a gas wall heater. Sorry, about $1,000, I should take that back. And then you had the, I should have done incremental costs. You can see instead of like, there's $20,000 there for taking the old one out and sticking in drywall and painting it over. It worked out $75,000. This is their cost. I didn't make this up. This is their table. 75 grand is what they saved by not putting in new gas wall furnaces. It was also far more efficient. The Title 24 numbers worked out way better by going to a heat pump, even with electric resistance, an air conditioner with electric resistance. So in every way that we went down it, but the most important was first cost. So when you go over to the water heaters, you see that to get a 370% efficient electric water heater, it costs in the range of retail. Wholesale, they're $900. Retail, they're more like $1,200 to $1,300. Now, in on-demand, that's 90% efficient. There's a whole bunch of products there from different manufacturers, so you can see a range of pricing. It's about the same cost. It costs more to install, it costs more to vent, it costs, I already did that for you. But the actual product is about the same cost. But the efficiency, people, 90% versus 370%. So, if we were to talk about what's available in other parts of the world, the Japanese have explained to me on multiple occasions, Mitsubishi said this, Fujitsu said this, that they don't import their high-performance products to the United States because we don't care enough about efficiency. But look, there's Panasonic with a COP 5.1. That's a 510% efficient heat pump water heater. It's from Panasonic. That's one of 9 different products available over in Japan. 9 different manufacturers, I meant to say. Dozens and dozens of products. But their efficiency is in the range of 400 to 570% efficient. In the United States, we're between federal minimum is 200% efficient, and we see products up to about 350% efficient. I have a 400% efficient heat pump in my house. Those also are available. Now, on operating costs, DOE yellow tags, I realize you can't read those numbers. The point is, up on top, you're gonna see heat pump water heaters. The lowest cost of them is $114 a year to operate, according to the yellow tags. Now, on a gas system down below, the least cost is $202 for the A.O. Smith product line. So that's for the highest performance product they sell. So it's about twice as expensive over a year to operate to get the best gas product you can buy. Now we're shifting to operating costs from first cost, which, say it again, the nation's electrifying because of first costs. But it's better for consumers if you electrify also. Now, a case study of how this works out in the real world. I've got 4 different apartment complexes I'm working on right now. I've had to do this analysis every single time with 4 different developers, 4 different general contractors. This is a very authoritative table I'm giving you based upon real construction costs. And what you can see is that we have on the left-hand side 3 different ways to put in a central heat pump water heater, some with more storage, some with more production of BTUs. So you see a range of pricing between $3,400 up to $4,600 for putting in a central system, depending upon how you configure it. Now, if you go over to an individual tank heat pump water heater, it's down to $3,000 per unit. And if you go to the gas system, it's $3,500. So the gas system is more expensive than the 2 least cost heat pump options, both central and individual. Most of that gas cost is in the gas system delivery. This is an existing bare lot in Los Angeles, or an existing lot in San Jose, or we're talking about one over in Washington, D.C. And they have to deliver a gas line to the building in some way, this new place they're going to do it. And it's about $100,000 for these big buildings. And more than doubles the cost of the gas boiler that you put in. So that's a real cost that developers pay. Many of you guys don't include the lateral cost or the meter set or putting the gas through the building in your analyses, which is a deficiency that a construction project manager would never allow, because there's hundreds of thousands of dollars of work to be done there that they actually have to pay. So this is an important thing I'm trying to bring forward to you. The gas delivery, which is a real cost of burning gas, is a very large cost in the real world of construction, and people are avoiding it as best they can because it's too expensive. Now, moving away from why do builders electrify to some of the more operating elements of it around storage, grid stability. So my physicist partner, Michael Winkler, has been leading in thermal storage for 20 years in the United States. He goes to conferences, he speaks on it back in the days. Now I go to conferences. And he says, what we do is thermal storage for thermal loads, electric storage for electric loads. There's reasons behind the efficiencies of that. So what does it look like in the real world? You take heat pump water heaters, that's a thermal load, you make them store it thermally. You can do a central system like that Airmec there, or the Colmac I showed in the previous picture, or lots of other products. And you try to store your energy needs in the water as heat, because you're delivering heat. It's a low-grade type of energy, you don't need to elevate it up to electricity, just keep it as heat. Now on the electric side, the biggest battery, the most cost-effective, I want to bring that forward, the most cost-effective battery you have is your car battery. It's in the range of 30 to 130 kilowatt hour, or 130 kilowatt hours stored in it. That's bigger than the 5 to 10 kilowatt hour battery that you might buy for your house. You might have that battery for your house for maybe for grid arbitrage, but most people want it for resiliency. You know, earthquakes, wildfires, tornadoes, tsunamis. Go down a long list of things that disrupt power systems. A bad hurricane. That can be met with a car where you can have your whole all-electric house hanging on for 3 days to 2 weeks just on the car battery. If you had a solar array, it goes on and on and on and on. And your car battery is just helping you out at night. That's your cheapest battery. That's what Japan deployed after the tsunami in 2011. Nissan, Mitsubishi, they took their existing electric cars and they said, because we just shut down 1/3 of the power supply in our country, we're going to make sure your car can do this job of providing you energy at night in a cost-effective way. It's a terrific, cost-effective way to go forward. Is to just use one battery that's big, drive it someplace, charge it up, bring it home. Ideally, you charge them up at work where there's a big solar array, come home, charge off of solar power, use it at night. Obviously, not home during the day for most people. So you want to have that solar array on the places where you're going to during the day. So, zero net energy, where we add solar to the electrified building, that was cost effective long ago. What I have here is a list of construction costs, add-ons, based upon the 2008 code in California. So what did it cost to do zero net energy then, similar to Jern's slide? It costs an extra $3,000 in heat pumps, it costs extra $250 in inspecting everything, make sure it's done right. There's a $10,000 solar array per apartment. And it costs less to put in the heat pump water heater. This is real construction costs. And a little bit more for the installation. It costs about $12,500 per unit to make it zero net energy. And most of that was the solar array. The solar array paid itself back in about 6 years. This is a 55-year asset that they own. So there's a long time that they're profitable. But the nice thing about it is that they actually get the money right off the bat. As you lower the utility allowance and affordable housing by $60, you raise the rent by $60, People are more resilient, they've got a solar array during the summer. There's so many benefits to solarizing. And you solve the split incentive by raising rent. In the same way in your own home, you don't have a split incentive, you get the benefits. So they get a loan at the end of it called the permanent loan. The permanent loan is based upon your rent. If your rent is $60 more, you get all that money up front. And so they made nothing, but there's a $10,000 cost to make it zero net energy, but they won. They won competitive funding from CTAC, they won competitive funding from the USDA, they won on cost competitiveness, their construction costs were lower, their efficiencies were higher. There's no cost to them, but there's so much profit. They got to do a project in a rural area, and the reason why they did this Republican-owned, Republican-controlled organization that's mercenary in their business practices, is because it made more money. It's just that. I want to show you how that works with other developers. Oh, on the right-hand side, you don't see that. The little apartment complex down there in the lower right-hand corner, they made $300,000 on a retrofit solarizing it with that same financing strategy. They made hundreds of thousands of dollars in profit. Another politically conservative, business-oriented company. And those are my favorites. I don't want environmentalists. They don't know numbers. I want construction folks who care a lot about what it's going to cost. And that's how, when they see that there's a $300,000 profit at the end, which is usually what I can promise as an affordable housing developer, it's going to be a few $100,000 that you're going to make more than you would have before. So we just churn through this. This is my business model. I work for developers. I try to help them understand how they'll save money. Now, the solar array, many of you would say, like, well, you know that solar is the cheapest kind of electricity. You can't buy cheaper electricity than getting a solar array right now. So what do you do when a building is tall? What do you do when a building's got compressor gardens on the roof? What do you do when there's vents all over the place? You elevate the solar array. Is that more expensive? It's 7% more expensive per kilowatt. It's a very tiny marginal increase to raise the array about 10 feet above the ground as opposed to having it right on the roof. And that's an important thing because you can get twice as much PV out of a roof if you cover the compressor garden. That's a real project that's going up in LA, by the way. On the right-hand side, that's a judicial building in Fort Aspen, I think, Colorado. It's just a nice visual for how you do a canopy solar array that doesn't have much impact from the street. They painted the underside white so it blended with the building. They stepped it back from the facade so you couldn't see it very easily. So, are they zero energy? Are they zero carbon? We have 265 multifamily residences on second-by-second monitoring. Individual loads are all monitored with CTs, are 1% accurate to the grid. I'm going to show you what science looks like here. So people have a very erratic behavior. Those are the people's apartments. Notice though, in orange and in blue, those are the average consumptions for two different apartment complexes composed of those little wiggly lines. Note that people, on average, are almost identical in their behavior, and individually are radically different, 10-to-1 ratio, every single day different, in identical apartments, with the same household population, with the same income. Affordable housing is very regulated, so you can really narrow down all the different chatter of discrepancies between households. They're the same household, same income, same population. They behave very differently every day, but on average they look almost the exact same in two different apartment complexes. The black line is the average of those two. Multifamily in consumption by occupants is just 1 kilowatt hour per day more. So you start at 13 for a day, and you go up to 19 when you have 6 people in a household versus 1. So 13 kilowatt hours a day for one person, 19 for 6 people, 1 kilowatt hour per person as you go up. The first apartment uses 13. The least efficient situation you can have is 1 person in 1 building. People talk about population. It's not population, it's underpopulation of buildings. That's the problem. We were putting far too many people into big homes, small homes, whatever home, by themselves is terrible for the environment. It's not people growth, it's the building growth without people in it. And when you see, a lot of you guys are probably concerned about HVAC energy. It almost doesn't exist in apartment complexes that are built to high performance standard. This is not Passive House, this is just Energy Star 2014. So in red, that's domestic hot water. In gray, that's the plug loads I just showed you. Then you go to cooking, and then you go to lighting. Then you go to the refrigerator, and then you're at the HVAC system. This is the actual monitored loads. And finally, you get to the dishwasher. That's how a zero energy apartment complex functions. And so we focus a lot on domestic hot water because that is the 25% of the load of the building, not the 4% of the load building, which is HVAC. And you can see this is different sizes, the 1 bedroom, the 2 bedroom, the 3 bedroom, very consistent results on how that works in the real world. Now, last slide here. On the left-hand side is one of those apartment complexes in Dixon. It's close to Davis. It's 59 townhomes. And you can see on the left-hand side how the electricity consumption went over the years. So pretty much starting in April, it's a zero net energy site every day kind of project. But once you get into the winter time on the left and the right-hand shoulders of it, you can see consumption, net consumption going way up. So we asked the question, given the actual carbon balance of our grid every hour, this is an hour-by-hour analysis on the right-hand side, we can say that over a year, this entire apartment complex was 94% zero net energy and 99% zero carbon. Jerry's point earlier in the day that a zero net energy apartment complex can look negative carbon intensity. If we'd had 2 heat pump water heaters that hadn't gone into the electric resistance default mode, this would be 100+% zero carbon facility. It was only because 2 water heaters did something. So solarizing a building can get you past zero carbon to negative carbon. You can offset more than you're consuming. For the cheaper cost, the best price is to go this way. You electrify it, and then you get cheap electricity in the form of solar panels, and off you go.